Welcome to Lesson 9F. I can solve advanced problems involving arc measures and segment lengths. So we already know how arc measures relate to central angles and inscribed angles, namely that a central angle is equal to the measure of the arc. So central angle AOC is 70 degrees, therefore arc AB is also 70 degrees. Whereas an inscribed angle is half of its arc measure. So the measure of arc AB would be 2 times that 35 degrees, which is a central angle, or 70 degrees. So when we're looking at intersecting angles formed by two intersecting chords, what we effectively have are angles that these two angles will be equal, right, because they're vertical angles, but their intercepted arcs are not the same. Notice that 60 degrees is actually the average of 70 and 50 degrees. This is not a coincidence. The intersecting chord angle theorem states that if two chords intersect in the interior of a circle as shown below, then their angle of intersection is related to their intercepted arcs as follows. Namely that x degrees is going to be equal to the average of A and B, right? So angle x is equal to A plus B divided by 2. So let's do some examples here. I want to find arc BCD, or angle B, or arc BCD. Well, BCD is this right here, and notice it's being intercepted by the intersection of these two pieces here. And if we notice, that central angle measure there is 92 degrees. So I know that the 92 degree angle, that angle, the intercepted angle, intersecting chord angle, is equal to 34 degrees plus the measure of BCD, all divided by 2. So I multiply by 2 to clear the fraction, so I get 184 is equal to 34 plus measure of BCD. We subtract the 34 to get that 150 degrees is the measure of arc BCD. So we're using that theorem. Now if I want to find PQR, angle PQR is this angle right here, and it would be equal to the average of this piece and this piece. Well, I could find this. If you look, we've got all of the angles here in the circle except this one piece here, so I can find this by doing 360 degrees minus 180 plus 90 plus 60, and when I work this out, I'm going to get 30 degrees here as that angle. So this right here is 30 degrees. So the measure of angle PQR is going to be 30 degrees plus 60 degrees divided by 2, or 90 over 2, or the measure of angle PQR is 45 degrees. All right, moving right along. So we then have exterior angles, which are formed by two secants intersecting. So notice this is different because my intersecting lines are now intersecting outside the circle, and a secant is a line that contains a chord. Otherwise, it's a line that intersects the circle exactly twice. So in this picture here, I've got my secant angle, my exterior angle here is 20 degrees, and then the two intercepted arcs are 35 degrees and 75 degrees. And so this pattern, if you look, if I were to subtract 75 minus 35, I'd get 40, and 40 divided by 2 gets me 20. Another way to look at it is that 35 plus 2 times this angle gets me to 75. So if I've got two secants intersecting, then the measure of angle x, that exterior angle, is actually now a subtraction problem. It's the larger arc minus the smaller arc divided by 2. Or another way to write it is that that exterior angle is equal to my large arc minus my small arc divided by 2. So if I'm doing this problem here, I've got that angle, he's 30 degrees, and the large arc, I don't know, but I know my small arc is 50 divided by 2. Multiply both sides by 2 to clear the fraction. So I get 60 equals x minus 50. Add the 50 over to get that 110 is equal to that larger arc. So this guy here would be 110 degrees. Check your work. 110 minus 50 is 60 divided by 2 gets me back to 30. So that works. There are more cases of this theorem, but as a matter of fact, this ends up being the exact same case. Here I've got two tangent lines intersecting. I would still do x equals b minus a over 2. Same thing here. This is a secant line and a tangent line intersecting. It still follows the exact same pattern. So let's do an example here. Now I've got angle K is formed by two tangent lines intersecting, where this intercepted arc here is 240 degrees. Well, we know that all of the degrees in a circle, all of my arcs must add up to 360. So arc JL, the measure of arc, that should be L, not C, guys, sorry. The measure of arc JL must equal 360 minus 240, or 120. So this piece right here is 120 degrees. So if I want to find the measure of angle K, K is going to be the large arc, which is 240, minus my small arc, which is 120, divided by 2. Well, when I do this, 240 minus 120 is, again, 120 divided by 2. So the measure of angle K is 60 degrees. All right, let's keep going, guys. So now we come to the intersecting chord theorem. And what the intersecting chord theorem says that if two chords intersect in the interior of a circle, then the product of the segments of one chord is equal to the product of the segments of the other chord. Or really, so the segments of one chord, I've got AC and CE. So AC times CE would equal, the other chord is BC times CD, BC times CD, okay? Why is this so? Well, if I were to connect some lines here, if I were to connect AD and BE, I actually end up creating some similar triangles where these angles would be congruent. We'd actually have a triangle congruent by AA tilde. So we end up creating two similar triangles when we connect those segments. So let's do an example here. If I know that A to E is 11 and E to C is 8, well, again, guys, if from A to E is 11 and this is 8, that means A to C must be 3. And then I know that DB, so that's my whole length here, is 10. So from here to here is 10. And CD is X. Well, that would make BC 10 minus X. I want to find the value of X. So I'd set that up. I multiply the two pieces of one side, 3 times 8 equals the two pieces of the other side, X times 10 minus X. So I distribute, I get 10X minus X squared equals 24. Because this is quadratic, I want to pull everything over to the same side. X squared minus 10X plus 24 equals 0. This is factorable. Two numbers that multiply to 24 and add to negative 10 are negative 4 and negative 6. So it'd be x minus 4 times x minus 6 equals 0. That means x could equal 4 or 6. And when I check that out, if I let this be 4, that would make this piece 6. Whereas vice versa, if I let this be 6, this would be 4. It still works. All right. Let's keep going. So, there's also a relationship for how secants relate to each other. And that relationship is, well, if you look here, it's AB, that's from here to here, times AC, that's here to here, is equal to AD, from here to here, times AE. Well, let's break this down into some language that's a little bit easier to understand. What it is, it's that the outside segment times the whole is equal to the other outside segment times the whole once again. Outside times whole equals outside times whole. So let's do an example here. If I know A to B is 4 and B to C is 6, well, that makes the whole here 10. I want to find the length of, oh, and D to E is 3. I'm going to let AD be x, which would make my whole be x plus 3. Well, let's solve this, shall we? So, side with the green, it's the outside piece, which is 4, times the whole, which is 10, equals, on this side, my outside piece is x, times my whole, which is x plus 3. We're going to distribute, so this becomes x squared plus 3x. My other side is equal to 40. So I want to subtract that over, so I get 0 equals x squared plus 3x minus 40. I want two numbers that multiply to negative 40 and add to 3. So I like positive 8 and negative 5, so I get x plus 8 times x minus 5, okay, equals 0. So it means I get x equals negative 8 or positive 5. Well, I don't like negative 8 as a solution because I can have a negative side length, but I do like the 5, okay? That would mean that this piece here is 5, and this piece here is 8, and 5 times 8 is 40, just like 4 times 10 is also 40. So I get x equals 5. All right, guys, that's the end of our video. Thank you very much for watching.